So at the end of our last class, we had begun our exploration of the concept of a knot invariant. Remember, a knot invariant is a property that we can attach to a knot, to the three-dimensional entity of a knot, that we can discern through any two-dimensional diagram that we could draw of that knot. Right? Any property that we can tell from a diagram, but which actually represents a property of the knot itself, is called a knot invariant. And so we saw a few examples of those kinds of properties. For example, we saw some examples of things that were not knot invariants. For example, the total number of crossings in a diagram does not actually tell me anything about the knot itself, because we can have multiple different diagrams of the same knot, for example, even the unknot, which have different total numbers of crossings. But those properties which are invariant are the ones that we kind of most care about. And so an example of a knot invariant might be something called, here's a fun example, it's called the stick number. This is how many toothpicks would I need to have? What's the smallest number of toothpicks that I would need to have in order to lay them down on a table and form a diagram of my knot? Right? Imagining that the toothpicks are as long as we need them to be, but just how many of them would it take for me to make a diagram? I think we can actually look in the knot info database. It actually lists stick numbers for knots. We just have to ask it to do that. So let's do that. So stick numbers. So for the trefoil, for example, the simplest example of a non-trivial knot, the stick number is 6. You might imagine for my trefoil knot that I could make a diagram out of this just by kind of, squaring off making some corners over here. So kind of each of these arcs becomes kind of 7-shaped, like 2 toothpicks, and we sort of arrange them in a way that makes a total of 3 crossings. So 6 is the smallest number of toothpicks I would need to make a trefoil. So non-invariants are what we want to study because they give us ways of they're almost like summary statistics in a way, in the same way that a summary statistic kind of summarizes an entire messy looking data set of numbers. A knot invariant is kind of a summary piece of information that tells us something about the three-dimensional knot itself, even if that invariant usually doesn't tell me the whole story. For example, there are a lot of different knots that have a stick number of 8, right? All these 5 and 6 crossing prime knots all have a stick number of 8. So that number is the same, but those knots are all different, right? Some of these knots are 5 crossing knots. Some of them are 6 crossing knots. We could show, presumably, using Reidemeister moves that, this knot 5-1 and this knot 5-2 are not actually the same knot. There is no isotopy from one of them to the other, and yet they have the same stick number. Right? So even though the stick number is an invariant for knots, it can't tell the whole story because it can't tell these different knots apart from one another. They have the same stick number. So what we want to do then is embark on a quest for more and more sophisticated kinds of knot invariants. The stick number seems like it's pretty crude, right? It's not able to tell apart the 5-1 knot from the 5-2 knot, from the 6-1, from the 6-2, and so forth. And so the more resolution that we want to get in our knot invariants, the more capability to differentiate between different knots, probably the more complicated our invariants are going to have to get. And so generally the sort of history of knot and invariant theory has been a history of kind of trying to build more and more algebraically, geometrically, topologically interesting and complex examples of invariants so that they have the ability to tell the difference between more and more different kinds of knots in a search for what we might think of as like a Rosetta Stone, right? Out there's probably some kind of invariant which has the ability to tell every different type of knot apart from one another. Right? But that would probably have to be something pretty scary and complicated because there are so many different kinds of knots out there. And to be able to associate to every different knot in one-to-one correspondence a different kind of algebraic structure seems like a daunting task, and it is. But we're going to get most of the way there today. If we can get through the whole agenda that I kind of have in my mind for us. We'll see what happens. So I want to pick up, because this is going to be where we sort of get a foothold in how to make invariance into a more algebraic question, by thinking about coloration once again. So one of the more interesting and sort of noob-friendly kinds of invariants for knots are colorations, ways of assigning colors to the arcs of a diagram so that at every crossing in that diagram, either all 3 colors that meet at that point are the same, or all 3 colors that meet at that point are different from one another. right? So the one thing that we can't have happen is for two colors to be the same, but the third one to be different at a crossing. As long as that doesn't happen, then we have what's called a valid three coloration for a knot diagram. So the trefoil, for example, has a trivial three coloring where we just color everything with the same color, but that's not interesting because we can do that with any knot. What is interesting is the question of whether we can color the knot with all three different colors and still get a valid coloration. And in the case of the trefoil, the answer is yes. Right? For example, this coloration meets my criteria that at every one of the three crossings, all three colors are either all the same, which in this case, that doesn't happen in any of my crossings, or they're all three different colors. And that is what happens at all three of my crossings on this diagram. So the trefoil is an example of a three-colorable or a tricolorable knot. And we can show that tricolorability is a knot invariant. And so because it's a knot invariant, if one diagram of a knot is tricolorable and another diagram is not tricolorable, so try as we might, I don't think we're going to find a way of tricoloring this particular diagram. So if I can't tricolor this diagram, then it must not represent the same knot as this diagram did, right? If tricolorability fails in one diagram and succeeds in the other one, because it's a knot invariant, that must mean those were different knots in the first place. So what we ultimately want to do is try and make colorability into an algebraic question, right? Because we want something better, something more sophisticated than just guessing and checking to figure out whether we can actually successfully tricolor a knot. Or more generally, if I have more than three colors in my box of crayons, maybe I have K different colors in my box of crayons, can I color my diagram using all K of those colors subject to these same requirements, right? That at each crossing, either all the arcs have the same color or all three of the arcs at that crossing have different colors. So our validity criteria remain the same, even when we have more crayons to work with to color in the arcs of our diagram. We can show that K colorability, like tricolorability, is also a knot invariant. And so this is the thing that we want to figure out how to make into an algebra question. So here's where we pick up the story. What we want, ultimately, is a way to write down an equation, let's say. An equation in three unknowns. Let's call them X, Y, and Z. And these unknowns are going to be, we're going to think of them as the colors of the arcs that come together at a given crossing in a knot diagram. So maybe X, Y, and Z take values in the set red, green, blue, or maybe they take values in a set that has 5 colors in it or 10 colors or something, right? And we want an equation, an algebraic equation that's capable of satisfying these colorability criteria, right? That either all three are the same, so either X is equal to Y is equal to Z, or if that's not the case, then X, Y, and Z all need to have different values. Can we find an equation that meets that need, that can mimic these two criteria for colorability? So that's where we're going to start the story today. What I have here are three different equations in the unknowns X, Y, and Z. And the thing I want you to think about with your team is, first of all, which of these equations is definitely going to be true whenever X, Y, and Z are all the same? And then which one of these equations is definitely going to be false in the case that we want not to happen, where X and Y are the same, but Z is different from the others. So three different possibilities here, equation 1, equation 2, equation 3. With your team, take about 15 minutes or so and figure out which of these equations is definitely true in the case when the three colors are equal, and which is definitely false when two of the colors are equal, but the third one is not equal to the others. If we have such an equation, then that equation would be capable for us of mimicking the criteria for a valid coloration. So there was no fooling you in this activity. You notice that all three of these equations are satisfied when X, Y, and Z are all the same as one another. For example, if X, Y, and Z are all equal to X, right, then in this first equation, X minus Y is going to turn into X minus X, and it's just going to wipe out the whole left-hand side, and the equation is satisfied. Same thing with X plus Y minus 2Z becomes X plus X minus 2X, which goes away, that becomes 0. Same thing with number 3, X squared plus X squared minus 2X squared. So all three of these equations have the power to be satisfied when the three colors of my arc meeting at a crossing on my diagram are equal. And so the question is, which ones of them can also be satisfied exactly when all three are either the same or all three are different? In other words, which ones of them are going to break? Which ones are going to fail in that case where we want them to fail, where two of the colors are the same, but the third one is different? So what you noticed about the first equation is that the first equation, if x and y are the same, it doesn't matter what z is. Right? Because if x and y are the same, this first factor, this x minus y factor, is automatically going to be 0 and 0 out the whole left-hand side. So this first equation does not discriminate in the case where x and y are equal and z must be different. That's not necessarily true. If x is equal to y, then it doesn't matter what z is. Z can be absolutely anything. We have a slightly less profound violation going on in the third example, x squared plus y squared minus 2z squared equals 0. If x and y are both the same, then we get something like 2x squared minus 2z squared is equal to 0. But as your teams noticed, we can still make that equation true even if z is different from x and y just by making z equal to the opposite of x and y. Like if x and y are equal to 2, and we can make z equal to -2 and still have that equation be satisfied. So nothing in here said that we're going to consider the positives and the negatives to be the same in some way, right? We want this equation, we should be able to put any kinds of integers into it, right? And so if this equation can't tell the difference between z equals 2 and z equals -2, right, then this is probably doesn't have enough power to be valid when we want it to be valid and for it to break when we want it to break. The only equation in this batch that does is the second one, x plus y minus 2z is equal to 0. It also happens to be kind of the simplest one, which bodes well, I think, for our algebra today. So x plus y minus 2z equals 0 is satisfied when x, y, and z are all equal, and it is satisfied when x, y, and z, well, it might be satisfied when x, y, and z are all different. It kind of depends. That's kind of a flexi point here, right? You can easily think of examples where x, y, and z are all different integers, and yet this equation is not satisfied. But we do know that this equation definitely breaks. It's not possible for it to be satisfied if x and y are both the same, but z is different, right? This equation is definitely going to be false in that example. If x and y are both the same, then z must be the same as x and y in this example, which makes this the one that we think is going to have the most legs for us today, as far as an equation that can tell us something about the colorability of a knot using its diagrams.